Caxias do Sul é uma universidade comunitária que tem como missão produzir, sistematizar e socializar o conhecimento com qualidade e relevância para o desenvolvimento sustentável. Sua vida e seus sonhos. Cerca de 100.000 pessoas levam no seu currículo o nome da Universidade de Caxias do Sul. Mas o legado de uma universidade não pode ser só medido pelo número de pessoas que ela formou, mas também pelos conceitos e ideias que ela ajudou a revolucionar, pelas empresas que ajudou a implantar e até mesmo pelos sonhos que ela ajudou a concretizar. A marca da UX ultrapassou as barreiras do tempo e os limites do espaço. Ela está impressa em milhares de histórias e conquistas e segue sua trajetória de sucesso, preparando pessoas com capacidade para transformar o mundo, criar o novo e antecipar o futuro. Universidade de Caxias do Sul.
Senhoras e senhores, bem-vindos ao UX Teatro. Atendendo normas e instruções do Código de Posturas do município de Caxias do Sul e do Corpo de Bombeiros, alertamos que é expressamente proibido fumar e consumir alimentos e bebidas nas dependências deste recinto. É expressamente proibido permanecer em pé no decorrer do evento. Solicitamos também a gentileza de desligarem seus celulares, bips ou outros tipos de equipamentos eletrônicos, bem como qualquer tipo de instrumento que emita sons e sinais sonoros. Agradecemos sua compreensão e desejamos um bom evento.
Good evening, everyone. We will have our first lecture now, the international one, with Rui Vu. We are glad to Rui for accepting our invitation to be here with lecture. Rui is an assistant professor of computer science at the City College, City University of New York, and an assistant professor at Center for Urban Science and Progress in the New York University. We focus in large-scale visualization, big data systems, and scalable displays. He is one of the co-creators of VisRails, one open-source scientific workflow and provenance management systems, where he led the design of the VisRails provenance SDK. So, Rui, please.
Thank you, Claudius. Good evening, everyone. Thank you very much for attending my talk. It's really truly a pleasure for me to be here and sharing my research experience with everyone. Some of the work that I've done in visual analytics and in the space of big urban data. So as Claudius already introduced, so my research background is in large-scale visualization. But if there's one word to describe my research, I would say I'm a system builder. So I build systems. Right? So if I have more time to describe my research, I would say that I'm working in the intersection of visualizations and big data analytics. By that I mean that I truly work on developing scalable techniques and algorithms that actually supporting large-scale visualization and analysis. In the past 10 years or 15 years, I have been working on streaming algorithms, big data management, as well as some work in parallel distributed computing. So actually, I starting out at NYU and CUNY in the past for 3 years. I started as we have a small lab called Big Data Interaction Lab. This is a very young lab. It's only started since 2015. We have about, so I'm leading this lab. We have about 5 PhD students. They all from different backgrounds and 1 undergraduate. So even though, because it's a very new team, we're actually learning a lot from each other. So I learn from them, they learn from me. But one good thing is that we're really enthusiastic about doing research in this area. So one of the direction or the mission that we undertake is that we would like to reach out to domain experts. So all our research, usually we don't just work in the theory or just in computer science. We take those technology or techniques and apply it in the domains. That's why we really value our collaborations with other partners, such as NYU Center for Urban Science and Progress, where I'm a core faculty member there, and also the CUNY Advanced Science Research Center. That center, we have a lot of different science in structural biology, photonics, or environmental crossroads. So we work with them on problems, try to solve real-world problems to try to improve the life of citizens in the city. We also have some partnership with Building Performance Lab as well. So these are just some of the images that we have in our lab. We have some scalable displays, some tools, some mobile device. But I want to mention that besides doing all this type of visualization work, we also focus on big data analytics. We do time series forecasting as well as some applied machine learning, try to predict or try to detect events or anomalies. But for this talk, I will focus on visual analytics. Okay, so one thing I would say about our lab or our research is that we love data. So whenever we have someone, our domain expert, our collaborators have data, we just jump on those and try to collaborate. So before I came to New York, which is in 2011, I worked more in scientific data area. So we have a simulation of fire, of fighter jets, all those CAD model scan. We do visualization and try to actually do simulation as well. But when I moved to New York, we got exposed more to urban data. So these are transportations. These could be like cell phone data or human mobility that generate from your devices. So we took all the technique that we developed in scientific visualization or scientific computing and applied them into this urban domain. So here's just some example. We have some buildings, we have millions of them. We could have a lot of cell phone data. On top, we could have some large data set with just 27 billion voxels or 100 gigabytes. That's a normal data set for us. But when we really interested into data, so one particular objective that we really like to focus is that we would like to improve the quality and performance of visual analytics applications for big cities. Big cities mean big data for urban domain. By that, we want to work on big spatial temporal data. I'll explain more when we go to that, talk about big data and big cities. And we wanted to do in urban science or urban informatics. So in these particular applications, we would like to improve make the applications more effective, more efficient, more scalable, and so easier to use for domain experts. In addition, we would also want to make it easier for people in the domains to develop their own applications. So that is our direction in this particular area, which is the focus of the talk here. So I would like to explain first what I mean by visual analytics applications, because there's a lot of definitions, but what we mean by visual analytics is that all those applications that follow the visual analytics pipeline proposed by Daniel Kim almost 10 years ago. So the main purpose of these applications is that we have data, we build some applications, so in the end we can extract insight and knowledge and try to make a decision out of that. So in these applications, we usually start with raw data set, could be multiple or one of them. We do a series of transformations to extract the information that we would like from the data and prepare them for consumptions. And then we go through a series of data mining process to build models. The models here in the broader sense could be anything that automated data analysis. This could be a simulation, could be some visual computing, or could be some predictive model. We also do visual mapping of those data to have a visualization, an interface to help us to understand the data, as well as help us to complement to the modeling part. So which means through visualization, we could inspect the errors generated through the models, or sometimes when we have a really large data set or data collections, we don't even know what to look for in the data yet. We actually want to use visualization as a tool to explore the data and then try to learn what we have there, what's the patterns, what the anomalies, and then try to create some hypothesis. So in this sense, visualization and modeling really are complementary to each other in this model, in this pipeline. After that, the visualization taking user input, we come out as a knowledge. Those could sometimes fit back into the original process, say that these might not come up to as a final decision yet, we need more data. And then the process repeats. And sometimes this come out as a good, good result. We could use that as a basis for decision making. So in this pipeline, the data is very dynamic, both in visualization as well as in the way we create the models. So this is the class of application that we really try to target, try to improve in performance and quality. So actually they share a lot of similarities with information systems because we have data components. We also have the human component inside the pipeline, in this pipeline. And the procedures that part of the information system, those could be as we apply as the knowledge back into the data in the process. So, but what's the difference here is that we have visualization and modeling is a crucial part of this pipeline, which might not be a required component in information system. So in a way, I could say that we are not exactly working on information system, but we are the practitioners of information system. We use those a lot in our applications. Okay, so there's two parts. So we want to improve visual analytics applications in the big cities domain, right? So these are the type of application we really want to apply to the problems and why we really care in big cities. Because as we already know, most of us now live in cities. 50% of world population is in cities nowadays. And in North America, that number is already 50% and will rise to 80% in 40 years. And I checked the number on Brazil, it's actually 85% already, so which a lot of people in the cities, right? And they grow at a very steady state, about almost 1% every 3 years. So I don't really know, in 10 years, that could be to 90% easily. So the thing is that when really fast growth of populations in urban places or in cities will lead to a lot of challenges. For example, we would wonder whether our infrastructure will be able to sustain, to support that amount of population, amount of people in the cities, also with populations or pollutions or housing or transportation, so on and so forth. But the good news is that in these cities, we usually have enough sensors or enough data source to generate the data, even from our mobile devices as well. So these data really help us to understand the cities. This creates new opportunities for us to understand how it's performed at the moment and try to improve it in the future. So taking these opportunities, about 5 years ago, NYU and the city of New York, we started a center called Center for Urban Science and Progress. This center takes on exactly these opportunities that we would like to create a safe haven for domain experts and also for computer scientists, so where they deposit data from different agencies or from both private and public sector, and they deposit in a place very secure where they, the domain expert ranging from urban planners to social scientists or physicists, they work alongside us, computer scientists, to make sense of the data and to actually try to understand the city. So CUSP, where I'm part where our lab is situated, and so I'm part of the faculty there, we're using New York City as a lab. We try to run all experiments there, try to run data pilot, and try to run small projects and to evaluate the methodology. Hopefully, in the future, those can be applied to other cities. So that's our visions. We have a lot of collaboration and partners in academia where we can utilize the brain power, and also in the industry where we actually utilize the technology or the proprietary data source. We also, the key important partnership of CUSP is that we have close connection with the city agencies. So we have direct data stream going to our data facilities where in a very secure way so that we can actually work on the data. In addition, we also have a master program in applied urban science and informatics. In a nutshell, that is an applied data science program. We will focus on urban area. This is only 1 year program. It's going from summer to summer, really intense. But what really the outcome of that program is that we, because as part of the program, we have a capstone project for running from 4 to 6 months. So that, that's really, for every year, we usually have a project combining the faculty members at the centers, the students for the programs, and also some of the urban planners or city employees to work on the projects, try to work on small projects to improve the cities. I'm showing some of the example first, that what type of projects we do every year, right? So for example, this is one of the project of the student. In this particular one that we have, so in New York, rent is one of the most expensive items on for everyone, because food is cheap, but when you pay rent, it's mostly like 50% or 60% of your salary most of the time, unless you have a rent-stabilized apartment. These rent-stabilized apartments, they can stay very low rate, like almost like 30% or 50% of the market price. If you live there for a long time, and as long as you don't move out, you can actually keep that rent almost forever. So the landlord, they don't really like this idea. They really want, to get more rent, and so usually at some time they try to harass the tenants to make sure that there's some problems with the apartment, so they move out so that they can increase the rent. And the New York State Office of Attorney General, they really want to fight against these harmful practices. So they actually try to work with us and the students to create a portal, a dashboard, where their attorney or lawyers can actually go there and pull up a landlord profile. It will link up all type of data source, not just the direct owner of the building, but anyway, he has like some proxy companies, or he has some management company that goes through his name somewhere, linked to a building, and somehow he create a lot of complaints through these buildings. They will build a case against him. So in this particular project, we have 4 students, 2 faculty, me and another civil engineering faculty members, working with the team there at NYSOAG. We harness the data from 12 different data sets, about 40 gigabytes. We create this portal with visualization. We can type in the name and search, and so show all the complaints. The reason that I put 40 gigabytes plus is that this data set is really dynamic. They cannot be ingested directly into a database because it keeps changing. So they build a very dynamic data system, as shown on the right. It has some back-end components, some front-end components, some network communications. So in the end, this is a platform that we deploy at NYSOAG. It really helped them to build the case much faster than before. So before it could take weeks, now it could take just an hour to actually build up a case against someone they search for. So this is one of the custom projects coming out of the program just last year. So another example is that, so this one we actually working with the TLC, the Taxi Limousine Commissions, which mandate all of the car for hires in New York. So this one, so look at the problem here is that, so we have about 150,000 drivers in New York, counting Uber drivers as well, but there are only 69 relief stands. Relief stands are those that actually the drivers can go and take a rest, go to the bathroom so they can actually take a nap a little bit and go on the street again. So that's really, little compared to the number of drivers. They always complain. And out of those 69 relief stands, some of them really, underserved, some really overserved, depending on the locations. So now the TLC would like us to do a study, to see how to optimize the taxi relief stands. So we're using the data that all the breadcrumbs of a taxi and also the violations of parking tickets, because sometimes when the taxi driver really like a spot with a good food or good restaurant, he actually was willing to pay parking tickets just to go there and to take a nap and take a sleep and get out again. So here we're using 300 gigabytes of data, 4 billion data points of a taxi locations, try to see where they stop most of the time, how they move between different spots in the cities, and build a model through linear integer programming. We optimize the locations. So now, instead of all those on the right, we narrow down to those on the left only. So this is also another a small project from the master program. So this is yet another one I'm showing. So this is also another one we do is that, so this one is not with city agency, but with an association transit center. This is an advocate, non-profit organizations. So the bus in New York was known to be the slowest in the nations. But somehow the MTA website, which is managed of the bus in New York, they always claim that the bus perform really well, really good, always on time. So the metric that they use to say that they actually perform okay is that 80% of the bus that they put out on the street reach their destinations. That type of metrics is not really useful. It actually cannot tell us a lot about the cities, about the bus performance. So in this particular project, fortunately for us, they published the data of all the buses in the cities, every 30 seconds, location of all the buses. So we took that data for 1 terabyte data for the entire year. We learned about the patterns and built our own metrics for riders, also for board members, so they can look at these metrics and say that it's really slow. It's really have excessive waiting time. Using this data and numbers, they can take that and confront MTA, not us, actually the board members, because we don't really have no voice against them. So this actually, this project is really helping the agency board members, so we hope they will actually try to improve the city bus. So this is also another project involve a lot of data and of something helpful, right? So, so these are kind of some little success that we think that we have in the programs, but we have large scale data in here, but big data is not just about size, because actually if we're talking about the size or volume of the data, where people always say big data, 3 V's, volume, velocity, and then variety. So these research into big data already been done for past 20 years or 30 years. If you look to database system, HPC, it's been there for a long time. But the difference back then in HPC and in big data now is that, so back then, most of the data are stored on data centers, very few places. Those have really large machines. They have also a very good team to maintain the data and also to help the domain expert to build application like MPI to run across this HPC cluster. So data was in good hands back then. But nowadays, it's really common to have like 1 gigabit network. It's pretty much the norm in New York now. So after a couple minutes, I can go online, go through some data portals and download the data in no time. I could have like 30 gigabytes on my disk in just a minute, very quickly. Right? So now, the owner, like the one with the data now is not the expert. I don't really have like the skills to do like MPI, to do parallel program computing, or actually to combine all those things together. So, for me to go from data to knowledge as a visual analytics pipeline, I really need a lot of knowledge in visualizations, modeling, machine learning, or the math, all those stuff. Sometimes one person can handle all of that. It's actually a big issue for us. So this issue is true regardless of small or big data, right? But one thing we could do is that we could build applications. We could build applications to actually encapsulate all of that and to make it's possible to go from data to knowledge. So the pipeline that I was talking about actually try to encapsulate all of these complex process into a software that can reach to non-expert users. Okay. So that is about big data, but now we go to big urban data. Now we have the city component in there. It's even more complex now. We say that cities, we have like 3 big pillars of data source. First one is about infrastructure, all those about the road conditions, about the bridges, the tolls, all those things like that, like how the cities actually perform on the sensors. That's in one pillar. The second pillar is about the environment, about the pollutions, the noise, or about the weather. That's another type of data. And the last one is about the human, the data we generate ourselves. It's about Internet of Things, about our cell phone generated those, or social media, things like that. So to understand cities, we need to really combine data from all these three pillars together. But most of the time when we have a lot of data, we don't really know what type of hypothesis we want to look for or to search in these data collections. So it's really important for us to have a way to explore this large collection of data. So visual exploration is really important. That's what we argue for. Of course, there's all these data sets available in those open data portal. It's so many of them. For example, in New York, we have about 1,500 data sets available. The same thing for Chicago. I'm sure in Brazil, there's also the other data portals. So some characteristic about urban data. So we can claim that it's about either like translation or whether urban or not. But for us, as a computer scientist or the one doing computing, we treat urban data as anything with spatial and temporal components. And these, they could be like hundreds of millions of records, could be generated from taxi records, could be generated from your sensors, or the bus data, or about simulation as well. So anything that has spatial and temporal is our focus here. And our main objective in urban informatics is that try to discover trends and anomalies. In order to do that, we need to be able to query data really quickly, and also try to do interactions so user can actually interrogate the data in real time. So, but however, in order to do these type of queries, if we build in database, if we have some prefixed hypothesis, it usually doesn't work because the data is so large, so many possibilities. So for us, the ability to be interactive and to be able to explore dice and slide data depends on the conditions, different conditions, is really important. So number one thing for us, to help big data analysis, we need to be able to do things fast and also easy to use. So these things should be able to automate tasks from, for users, like if they do data transformations, we should be able to link that for the user already. And if they don't really know much about data, we should show some trends and anomalies and guide them through the process. And the users, we should assume that they have little or no computer science background, because these could be like, like social scientists or someone, some urban planners or government employees. For us to build applications support this type of constraint is that we need big data management and visualizations. So one motivating example is that, so we look at the NYC taxi data again. So this is really an interesting data set. So TOC, as I mentioned, is an agency that collecting the data. They've been collecting this data since 2008, 10 years ago. So every time everyone enters the yellow cab in New York, they collect the pickup locations, number of passengers, and then they record the destinations, the trip amount, the duration, so on and so forth. So each trip record has spatial temporal components of the time and location for both pickup and drop off. So there are two spatial temporal components. Along that has other things as well. So TOC been collecting this for a couple of years, and they have a lot of data piled up on their storage. They don't really know what their data looks like. Don't even know if they're clean enough or they actually perform well. So usually they just put on some on the cloud on some server and pull small piece of data out and look at 1 week at a time or subsample the data. But those doesn't work very well because sampling the data will remove the anomalies, only keep the trends. So they want us to build something to help them to build a tool to explore the data, dice and slide based on different time and locations. So the reason that I say that this data set is interesting is that even though taxi are just trip records, but with spatial and temporal components, they can act as a sensor to tell us what's going on with the cities. Because through the taxi data, we could actually tell, now look at the trip. At this time, going from downtown Manhattan to airport, for example, how long does it take? And if you look at weekends or weekdays, you will see where the hotspot of the cities are. Look at those population in the data set, right? So here's one example. We're showing like the number of taxi trips per day for 2 years in a row, 2011 and 2012. So the red one is 2011, and the yellow, the bluish one is for 2012. Even though they're from 2 years, different years, the patterns are very similar. You can tell that they shifted only by 1 day because the day of the week is shifted by 1 in consecutive years. So pretty much we have a habit, repeat the same habit for weekday and weekends for the entire year. And because they have very similar patterns, it's really easy for us to detect anomalies. So if we take a look at this plot, we see that in August 28, 2011, there's a dip. There's almost no taxi on the road. And also the same thing in October 28 too. I think so too, 28, that there's almost no taxi on the road. So for these, look at just this plot, we tell that maybe there's no activity on the cities. That was the case because there was 2 big hurricanes in the cities, one Irene in 2011, and the other one was Sandy in 2012. So no one on the street, almost no taxi. So by looking at this plot, we can tell what's going on with the city, just a pattern, the pulse of the city. The others we can also see like Christmas or Thanksgiving, and the special one on April 1st here, there was a driver strike similar to the one in Brazil because the gas price increased. So that's exactly what's happening there in the April 1st, the red line. So now if we go further, go from the temporal, just look at the temporal patterns, we go to spatial components. So now this is an extract of 4 hours of taxi data. On May 1st, 2011, we have from 7 a.m. to 11 a.m. every hour. So these are Manhattans, the blue dots are the pickup, and the orange dots are the drop-off. So from 7 to 8, it looks very normal. We have no normal activities for pickup and drop-offs. But from 8 to 10, the entire 6th Avenue, which is an empty road in the middle, empty. There was no taxi activities. This was because there was a fiber road bike tour, so they closed the road for no traffic there. So by looking at the micro scale, at the spatial components, we can actually tell what's going on with the cities, with the locations. So combine these two together, taxi is really a very powerful or strong data set can tell us about what's going on in the cities or the pulse of the cities. So that's why exploring this type of data really intriguing us. So not only we help the TLC to understand their own data, but also we're also helping ourselves to understand the cities in this project. So, let me go through a quick demo here. So the taxi data is really large. For each year, we have about 50 gigabytes. So when we have like about 3 years, it's about 150 gigabytes. So in our tool that we built for TLC, oops, where's that? Sorry. So this tool I already built almost 5 years ago, but it's always a pleasure to demo this tool because it actually shows the scale of the program. So here, I have 3 years of taxi data on my laptop. So after our old techniques, we can do all compression or indexing. It's about 30 gigabytes of data per year. So it's about 90 gigabytes on my laptop here. So I'm showing only 1 hour of 1 hour of taxi data. So all of the blue dots are the pickups and the red dots are drop-off. There's a lot of taxi in here, you can actually see, right? So this tool, we can actually browse through. We have them, you can browse through the time, like per hour, like this. Or if we're going further, for the entire week, we can actually see a lot more data. This is the number of taxi pickups and drop-off for 1 week. It's almost everywhere. It's really intense. It's a lot of data. Remember, we have like 500,000 trips per day, so a week, almost 3.5 million trips. So it's quite large. So the things that we actually help them is that the ability to do spatial and temporal queries right on top of the tools at very fast speed. So what I'm doing here is that I'm selecting all the trips starting from that region. This is called West Village, a very nice area in Manhattan. So doing that, I almost like instantly, do selection, can move things around. And the plot at the bottom shows the number of trips per day for that period of time. And we can also select another one, for example. So this one showing the different areas. This is in Upper East Side, for example. And we can also do like, origin, destination queries. This one go from here to here. So if you actually work with a spatial database, this type of queries can be really, really slow because they have to do a big join between two spatial components. But in our tool, we make it really, really fast. This is only for one particular week, but if we can increase, let's say, oops. So we also show the heat map, for example. Oh, one thing I forgot to show. Oh, one thing I forgot to show. So this is also the weekly patterns of all the taxi trip for the entire week. We can look at that and see that there's a daily patterns. And the interesting observation is that at 4 p.m., there's always a dip in number of taxi pickup. That is because there is a driver shift change. So if at that time we don't go the same direction with the drivers to the garage, they won't pick us up. So just want to mention that. So these also show the hotspot, different type of visualization. These are actually, Port Authority, Grand Central, and Penn Station, always crowded. Okay, so let's go further, let's say for entire year. So remember, for 1 year, we have about 180 million trips. That is quite, and 30 gigabytes of data is quite a large number of data. So if you remember, we have like the plot that have the 2 years overlapping on each other. To generate those plots using Python and just go through the data, it could take 20 minutes. But on the tool, we actually use, on this laptop, we use multiple threading and very fast indexing techniques. We actually compute this stream really quick. The time series here, and there's the dip on the Irene hurricane. We also can also do a very interesting reverse queries. So now if I select, let's say, the two main airports in New York City, this is LaGuardia and JFK, and I really want to know, after people arrive at the airports, where did they go? We can support this type of reverse query in our tool. This is also very expensive, so we select this one and say query here. So these are all the spots that I actually went through. But if we actually normalize a little bit, these are the top spot. So you see, even with 1 year worth of data, it's almost instantly query time. And one also shows two different trends for LaGuardia and JFK. So actually, these are the hotels. So they go to the hotels right after the airport. These are top hotels in the city, right? So I will do one more thing with this, and then I will switch. So give me 1 second. Let's pick just a couple hours. Oops. So in this tool, this kind of hidden features, I rarely demo this one, but I can demo this one today. Just to show the way we build system. So these are select all trips in small area, let's say this one. I can also show this type of animations as well. So we can also do if we have the route of the trip, this tool can also support the real-time rendering, so we can do those little clips of doing the animations. So imagine if we have a real route, it's only pick up and drop off, we can actually also do the full constructions. So this one I usually don't demo, but to show that it's a real system, it's not just some can demo. So anyway, so I will stop here. Okay, actually one thing I forgot. So besides just the location and the time, we also have all other attributes you can explore with the tools, like all 12 of them, like the trip, amount, or duration. People can go here and select the period, like time, and they narrow down, click OK. It also change the selections. So we let them do that type of selection. Okay, so I will stop this one. And go back. Okay, so using this tool, besides helping them to explore the data, this can be used to study mobility. For example, to study like the trip time from one place to from Lower Manhattan to the two airports. We can do side-by-side comparison. Or this one, we actually compare like the tip or the pickup in different area in the cities. Or we can also do like parameter explorations. So this is after Sandy hurricane, we want to look at the taxi activities in different areas in Brooklyn and Manhattan to see how they recover from the incidents. So this one saying that after the hurricane hitting on October 29, Manhattan is completely out until the end of the week, whereas in Brooklyn it recovered quickly right after the day, so it's 1 day after that. So the focus, one thing I want to highlight in this tool is that we have two things that we want to make it easy to use and want to make it fast. So the first thing is easy to use, the way we do visual queries. So instead of doing all of the query with SQL, we have specified the time in very tedious tuples and location in some weird names that we have to remember. So now we allow the users to specify those constraints right on our tools, and they do explorations or analysis right on top using the plots or do refine their queries. And for fast, so actually, as I mentioned, so we have about 3 gigabytes of data for each year on the laptop. To support that type of queries, we need to have very fast indexing techniques. So that is our contribution of this work in this particular work. So a typical query in our tool is that we have special temporal components. We say that we pick some locations, we pick some times, and we do a filtering. For this type of query, we have, I will skip some of these. We could use a database to support this type of queries, but let's say that we have now 5 years of taxi data about more than 800 million trips. Put that into a database like Postgres, for example, it could take almost 10 minutes to get one query back, because it's really large, a lot of data. It's almost 1 billion records right there, right? Or we put into commercial database that have very fast caching grid index. That one reduced the time to 20 seconds. This is really a big improvement. It's really good. This commercial database. But however, this doesn't actually get to like 1 second that we really want in this tool, because it's, for these type of tools, interactive. For these type of tools, we need to have very fast response time, because imagining if I draw something on the map and wait 20 seconds, it's really kill the user off, right? So for that, we design an index data structure based on KD3. This index data structure have very fast query times, and also the time to build the index also really fast. And the good thing is that it has very small memory footprint. So compared to Postgres or SQLite, just as a baseline, we almost like an order of magnitude smaller in terms of footprint, and we 1 or 2 order of magnitude faster in terms of query times. It's really important for our tools. But one of the things to highlight in this data structure is that we actually use that one to index all attributes, not just for the spatial and temporal. We also index like the trip, the tip amount or duration, so they can query on all those type of attributes. The reason that we actually achieve this speed is that we represent this one really in compact data structure. Instead of have 2 data components for each node of the tree, we have 2 because we have a balanced tree. And we also map that KD tree onto this block-based. That allows us to do out-of-core processing, and also allow us to only keep the one actually relevant in memory, but the rest on disk. And this data structure also works on GPUs, which is a big advantage for us. So using that, this particular result we're showing here, we take that same data structure, we extend to GPUs, we get also 2 orders magnitude faster than the commercial database, which is a big achievement. So this is just, I'm just showing some slide. That's why we pick KD3 over R3. So there's, R3 is mostly used in database communities, KD3 more in cryptographics. We use KD3 because we actually focus more on the query time and not really so much on updating times. So this one shows some advantage for us to using KD3. So, but the main disadvantage of KD3 is that updates does not maintain the balance. So for that, we have some workaround to actually to extend hierarchical KD3 to address the issues. So this one just proves that. So our KD3 is stored in 2 parts. One part is CPUs and one part on GPUs. So on the CPU side, we store the tree structure, and on the GPU side, we store the block base of all the actual data points. So we can query in 2 steps. First one is on the CPUs, we traverse the tree in that hierarchy order to get some relevant nodes that may contain what we really want in our queries. And then we send all those potential nodes onto the GPUs, and relying on the many cores architecture of GPUs to actually to do a fast filter. So this is, again, at least some of the advantage of our work, but some of these can actually be found in our papers. I can refer to that. Okay, so this is just highlight again. So we take that data structure, we now extend to open source MongoDB. We run on taxi data again. We have almost like 3 orders of magnitude faster now, using that hierarchy hybrid approach. And also on Twitter data, besides taxi, we have a spatial temporal with the text messages. We also use that. So in our paper, we also talk about how we extend that one to support text index. I will skip it here because in interest of time. Okay. So one last thing about this index is that it also supports multiple GPUs. If you have 2 or more, it will take advantage of that. And it also handle that in out-of-core fashion, which means when we have more data than we can handle on the same machines, it can store things on disk and streaming data from disk onto GPUs. So it can support a large amount of data. Okay, so this I really need to say that. So we're saying this, so some people will ask like why relational database are not as efficient as what we propose. We would say that actually they are very efficient. The things that we target on 2 different domains. So for database system, they don't really focus on interactive single queries. They focus on batch queries. So give them 1 queries, they may take 0.5 seconds. We give them 1,000 queries, that might take 1 second, because they optimize for that. There was no need for them to optimize interact queries, because they don't really build for visualizations. But for us, we really want focus on single interactive queries, so that's why we build the index and work better in our case. So this is another toy example. So an eye candy visualization. We're showing the taxi for 1 day. Pick 1 taxi. So the blue one is when it has passengers, and the red one is when it doesn't have passengers. We pick 1 and we go throughout for 1 day. So using the same tool too. So this one is saying that when they don't have passengers, they go really slow, but when they have one, they go really, really fast. And in 1 day, they cover for the entire Manhattan. So it's just for we can generate with the tools. Skip that. So beyond taxi fees, we're also using this data for other type of analysis. We're also using that to, for example, sometimes it's really, you don't need a taxi, you see them everywhere. When you need one, they are nowhere to be found. So this app actually using historical data, you can, using that data to say that at this time, which corner you should go and pick up a taxi. But nowadays, I think you guys prefer Uber more in this city, so probably it's no need anymore. But I'm very traditional, guys. I always go to yellow cabs. In New York, I never go Uber. Yellow, the hand waving, actually, feeling really nice to wave a cab in New York. So I only use Uber when I'm here. That's really strange. Okay. So we also using this data and build a ride-sharing simulation framework. This one, our strength in this work is that we actually, our system can simulate a very large scenarios with all type parameters, like a number of people in the car, the preference for each passenger, and we've done that using big data platforms. It can execute really, really fast. Like giving a 1-year scenarios, it can run on 1,000 cores in 20 minutes. So this one can really help like even urban planners or even like the TOC people to explore different strategies for ride sharing. So that is our work focus. And we also extend another work that actually using this data to study the human mobility. People move from one place to another. So at that time, we can see that what's hot in the cities. So those are different work. So we already talked about the building easy to use, building really fast. But other thing you want to mention is scalability, because no matter how fast or how efficient our index is, at some point it will reach the limit of my computer. It won't be able to support interactive speed anymore, right? For that is the limit of scaling up. So there's scaling up and scaling out. Scaling up is that we take a machine, we upgrade until we to the size of our data, until we support the speed performance that we really want. But there's a limit of the hardware we can upgrade. And then there's scaling out. When you have the limit of scaling up, you add more machines, do distributed computing, we can add more into the scene, right? So these are what's supported mostly by the big data. So we also go big data route, bring compute to the data with scaling out. So for now, we have like 4 billion records of GPS data. We want to do like unmet taxi demand. It's really hard to do on a single computer. We need the power of multiple machines. So for that, we actually have like, okay. We have a lot of questions, for example, like giving all these breadcrumbs of a taxi. So nowadays, we have a new data that every 30 seconds, every 2 minutes, we have the ping of the taxi. So we know where they are all the time in New York cities. So using that, we can learn like where they are when they are free to see where the demand and where are the supply to try to match them up in the city. But to generate one single map of all the supply at the moment, so this is for 1 year, we're plotting all of the taxi with their passengers for the entire New York. This particular map is a static map with Cardo DB, which is actually has Postgres on the back end. This one snapshot, one static visualization took 10 minutes to build, and it takes about 300 megabytes of database space for these visualizations. This is only one particular visualization. We have like everything in 1 week. What if we change now to Monday only, or to Wednesday only, or to weekends only, or to one certain area, or one to certain hours? We have to do a whole process again. So now the processing time is 10 minutes and 200 megabytes for each of the queries. It's really expensive. So we take a look at the pipeline. So this is what our pipeline we have using Spark. I skip the details here to do all the spatial join to build this type of visualization, right? But in the end, to put this to Cardo, that is a bottleneck. Is that going from the actual result to the visualization, it takes some time. So what we proposed, what we actually did is that we try to incorporate the tile rendering service into the big data platforms. So now we do in situ visualizations. So now after the visualization results, we actually do the maps, the tiles, to put on the map itself. So now we can actually do really fast interactive queries. So for example, this is our tools now. So now this is our, compared to Cardo, we can select any criteria like the time bins or weekend and weekdays. It will show right away on the maps instantly. And we also show the exact location of all the taxi for the entire historical data. It's really interactive. So this is our work in supporting scaling out the visualization of visual analytics. So we have more work in this area. This is actually one of the theses for one of members of our groups. So we do a special Spark library. Again, in interest of time, I will skip this piece. I think I'm almost out of time. Okay, so let me move to the second example. So let me see. I have time. Okay, I'm good. Okay, so so this is go to the second example. So before we look at the easy to use, fast, and scalability, so now we look more in the usability in 3D space. So in New York, it's all about the view. So your apartment is priced high or low, it's all about the view. And when we first enter a new building for office space, we pick the one with the best view. So view is almost everything. It's really costly in New York. So in this particular project, we work with an architect firms to actually, for them to understand visibility for different buildings in the cities. So if they have a new project in the cities, for example, like, so these architecture firms, they, when they have project, they want to first scout out different areas in the cities. Let's say this is a commercial building. So they will look for the place that actually have a lot of restaurants around so that the workers or the employees can actually go out and eat during lunch, for example. So for them to go through this process, they actually have to scout different reports on saying that a new restaurant is going to be out soon, or they know that some will be closed out really soon. They play by the ears most of the times. And those actually really tedious for the process, take a long time. So we would like to build a tool to help them explore the cities, look through different neighborhoods to see the characteristics of each neighborhood. And then after they select a neighborhood that's right for their project, we want to look at the what-if scenarios, which is now take my building and go to this area. I build a new building there with this structure, this height, and this architects, right? What change it will make to the neighborhood? We block some of the shadows, which actually improve the score, like translation, improve the price of the neighborhood, things like that. So they want to run what-if scenarios and pick the best one for their project. So we build a tool to help them to do this process automatically and use computer graphics and visualization to do this 3D computation. So in this project, again, there's two type of questions. First, the characteristic of a neighborhood, like what type of translation score, what type of education or spark or work score in the neighborhood. Is it suitable for children, suitable for employees or working populations, things like that. So we doing this, and the second one is, and the second one is that how a new development in this area will actually change the neighborhood. Those are the two type of questions. For this type of questions, we need data analysis in the first one, and we need impact analysis. Impact analysis is that we change the actual data to see how much it changed in the original the feedback loop in the pipeline. So I will skip some of this detail and go straight to the one. So for this type of, for the first one, for data analysis, we need to have different type of data in this tool. Is that the spatial boundaries, we need to have a different raster type data to say the crime rates or the translations or the location of the bus, for example. And then we need the 3D shapes of the building itself to give them a context in exploring the project. And then in the end, we need to merge them all together. And for the impact analysis, there's two types included in the tool. The first one is sky exposure. So when we put our new building, this is going to block the sky exposure to the place in the cities. For example, in this one, looking from the bottom up, this building will block most of the rays. Only those in the center actually get through the sky. But now we replace that with a new building, taller, skinnier. We block one more ray, for example. So this have a negative impact. And for this type of computation, we actually just do some computer graphics techniques. We move the camera to that location and render the scene at that location up. Now we just count the pixel of sky, and that is our metrics, our score. The second impact analysis is on the visibility. For this one, for each of the building, we can see, if we see the landmark, it's really a good apartment. Like we see the Empire State Building, or if we see the Statue of Liberty, those really good apartment. Then if I have a new building that blocking that view, then it's actually reduced the visibility of that building. So it's reduced the impact, the negative impact on that area. So for these computations, a naive way is actually go through each building and looking at the landmark to see how the new building changed the visibility. But this is very expensive because you have to go through all the buildings in the cities. So we do the other way around. Because if a landmark see a cities, if a landmark see a buildings, the building also sees the landmark. So now we go from the landmark itself and do a 360-degree scan of that landmark, and whichever building we see, we say that we can see that building, the rest are being occluded. So this is just some way to do it faster. Okay, so after we have all of the potential site and impact analysis, this is the tool we built so that they can actually look at this one and select which one is best for their projects. So the purple are the potential site. The blue is the one have positive impact that increase either the sky exposure or visibility. The red one are the one that actually has the visibility reduced, negative impact. So we, after that, we also have a gallery for them to select different type of buildings to put in there and have different impact. And for each of those buildings, we provide this gallery. We try to optimize for the view score. So these actually the data structure that we try generated by the machines. So these actually have very weird structure, but we will maximize the score of the visibility. So for this, some of those really weird looking building, but they say it's possible to build in reality, so it's okay for them, but I wouldn't live in that building. No, it looks really weird. Okay, so in the tool, we have this type to actually moving up and down for different levels, but I will show really quick for the visualization.
We're different. Why does a new building change the quality of a neighborhood and another doesn't? While the experience of a city is inherently subjective, the characteristics that shape the quality of it are not. To start to help answer those questions, we propose Urbane, a three-dimensional multi-resolution framework that enables a data-driven approach for decision-making in the design of new urban developments. Through a data-driven understanding of the existing and potential future city, architects, developers, and planners can better collaborate and make more informed decisions. The creation of Urbane posed several challenges. First was integrating 2D and 3D urban data sets from different sources and that don't share a format. Second was designing a system that could handle the sheer amount of 3D geometry that makes up a city. Next, to support urban scale spatial analysis, computation of measures such as view analysis and sky exposure have to be very fast to be integrated in the design and development process. Finally, creating a 3D interface that allows users to view and filter data sets and analysis at multiple scales. Urbane allows users to seamlessly explore the city based on multiple 2D and 3D data layers. For example, noise, crime, and is visualized here, subway access. The data can be explored at different resolutions, the city, neighborhoods, and buildings. The opacity of the 3D buildings can be controlled for better visualization of the data layers. Urbane uses a parallel coordinate chart that allows for easy and intuitive filtering of urban data sets. Here we filter neighborhoods for various attributes such as subway access and noise. The bold blue line represents the average of all Midtown neighborhoods. The bold red line is a user-selected neighborhood, here the financial district. Filtering of various attributes allows users to understand the characteristics of Manhattan neighborhoods. For example, the financial district and Midtown are very similar across most attributes. At the neighborhood scale, the same filtering system is applied to individual buildings. Again, the blue line represents the Manhattan average. Here, we filter individual buildings for attributes such as built area, crime, and noise, identifying sites for potential development. Once specific sites have been identified, Urbane gives users the ability to replace existing buildings with new buildings, testing different tower sizes and program combinations for the maximum zoned floor area. The user can generate speculative buildings on many sites. Here we see a hotel with residential, an all-residential building, and an office with residential. Once buildings are generated, Urbane can compute derived 3D attributes from the data in buildings. This includes the view from buildings to selected landmarks, the impact of buildings on sky exposure at the street level, and the impact of the buildings on the views of the existing context. This analysis can be used to evaluate the trade-offs between the value of a new development and its impact on the character of the neighborhood. This can facilitate the design and development process between architects, developers, and city planners.
Okay, so that is a video with our tools, because it's harder to demo on laptop. So to summarize the contribution of, that we have in that tool is that we have a very efficient way to compute the view and visibility score for each of the buildings. With the other tools, the architects have to go through a manual process. They have to load to Rhino 3D or the modeling process and export that to R or to MATLAB, run some small tests. So in order to test like 10,000 views at a time, it's almost impossible for them. I think it's actually impossible for them. And now if we do like the parameter space design, where we actually design different architects of the buildings to maximize the visibility score, then that is touching 100,000 of buildings design. It's impossible for a person to do it alone. So this tool really helps them to automate the process and make it easier for domain experts. So that is using 3Ds and the automated process. This is one our goal. So what's next? So what's next for us? So if we have a few successful case with the XIVs, with the urban and also some other projects. But if we look at the development time for each of these projects right here, so if we look at the XIV, it took us about 6 months to do the prototype of that particular tools. And the team, we have 5 computer scientists and we have about 4 analysts at the TOC to make that type of tool, right? And for the urban, we have like almost 1 year to get the first version up. We work back and forth with the architects, and the team also have 4 computer scientists and about 4 architects from the KPF, which is architecture firm. And another project that we actually have at the moment, we try to look at the 3D mobility coverage for cell phone towers in New York. This is actually a project that's going on with one of the telephone company. So we have like about 4 computer scientists working on this project. It's almost a year now. But one thing we could say that it takes a lot of time to build an effort to actually build efficient or useful visual analytics applications. It takes just a lot of time. And we want to understand why it takes us that much time. How can we improve the development time? So actually this is the example look at the 3D mobility coverage analysis. So those are the cone, the purple one, the brown one. I will skip that one. So these are the common roles in the visual analytic teams that we usually have, right? We have domain experts, domain scientists. These are the ones that provide guidance for the projects. It could be the architects or the TOC or the urban planners that we're working with them. And then we have some people, some experts on computing, on data, to how to do really fast data index, how to do data management, to integrate them all together. And then we have visualization experts. Those are design the visualizations and also to build a tool to actually to make efficient for people to explore the data. But very important components in all these tools is that because we always build custom rendering system for the urban project. If you look at the map, we have to start from scratch. We couldn't use Apple Maps or Google Maps because even though Apple Maps and Google Maps looks really nice in 3D, it can use for mostly eye candy of just eyeballing most of the time because you cannot change the building inside the map or to do impact analysis on top of those tools. So it's impossible for us to take Apple Maps or Google Maps put inside our tools to do this type of analysis. So in the end, the one that we show, we wrote from scratch, the mapping engines. We're using data from OpenStreetMap. And also for these types of developers that actually are really good at computer graphics, they also need to map all of the primitives from the data so they can actually visualize in a very efficient way. And most of the time, when we start a new project, we have to recode or actually modify a lot our existing rendering pipeline. So this is going a lot of effort in the last bullet right there. So in the teams always have data experts and computer scientists. So computer scientists plays all those 3 roles most of the times. So actually for all our projects it's like that. We have some of us actually know more about data, about visualization, about computing. Those are normal for data scientists. But for the last bullet, this is actually the pain point because these actually, most of the time we need someone really understand computer graphics pipeline and really understand visualizations, but not just understand that, also need to write them in a very efficient way because we need interactivity. So these actually are kind of hard to find expert in the team. It's kind of a pain point that takes a lot of time. So I have to say that actually I play that role for all the projects. So I do code a lot too. So I do play that role. It does take a lot of time. So even though I really want to play, to write code, I enjoy writing code for graphics rendering, I would prefer that I have a faster application development process so that I can have a new data set, new type of collaborators. I can put up an application in like a month or a week instead of 6 months. So our vision is that we try to get rid of this middleman. So I try to get rid of myself. So pretty much, these are experts and computer graphics specialists. It's hard to find. So in order to make, if we can actually remove that middleman there, so our data or our applications can reach to the users really much faster. So now instead of the architects go through me to have the new projects with the mapping engines, they just go straight to some student that know data science, know data analysis, and have a new type of applications much faster. So that's our vision. So now that's why we propose take a look again at the V's pipeline. So before we have data, visualization, model, and knowledge. So now this is the architects, the design of such applications. We have these 5 steps. We have data from GIS most of the time for 3D buildings. Then we have extract, integrate the data. We do some materializing of the geometry so that it can be rendered. For example, we have like a description of the road, 2 lanes. We take that, convert to like 10 pixels or 100 pixels, for example. And then from there, we build visualization using that data and also run some simulation scenario. One thing that I haven't mentioned is that in these interdisciplinary teams, Usually we have computer scientists working on different environments. When we have an application, after we developed, we don't just take that machine to go to show them. It's really not portable. So we want to send them an applications. So packaged application is also a big part of the pipeline. You have to do cross-platform because we run on Linux, for example. They have Mac, they have Windows. Then how you deploy the application on the environment that the data scientists actually or the domain expert worked on. So that is a big part of the pipeline. So the last piece, the last guy that the developers actually have to take care of those three pieces as a pain point as well. So taking these observations, we will have a candidate that we would like to use game engines to take care of those last three parts. Because game engine is actually feature-rich in rendering. It can do shadow rendering in some projects really quickly, and it usually includes the physics engines that can actually suitable for visual computing. You can write some code, some like compute shaders, and put it on GPUs or run on CPUs OpenCL. Those can actually be run really quick and parallelized easy. And just like Python or some other system, they have a lot of assets, which is packages you can use in your tools. And very important, but not to be slightly emphasize that the cross-platforms and hardware. So when you build an application in a game engines, they can run on mobiles, run on Linux, Windows, and the Mac. It's really a big win for us. So we consider game engines now as a way to actually, different approach to build this type of applications. That is our future directions. So, so our proposal is to build a plugin for Unity 3D. So our vision is that, so if a student in media program, which means the one that actually build a game or mobile apps, they can build a game in a week. We hope that they can work with domain expert, build another urban application in also a week. So now it's reduced the development time. That's our vision. We're going to leverage Unity 3D for rendering capabilities and to implement the visual computations and for cross-platform deployment. Those are the three parts. So this is our prototype. We start to move from me doing all the coding, go to an environment. So this is our simple plugin. We just barely started. So it needs a lot of work. So here, our vision is that go into this system, you click create cities, it will create all the basic data layers from OpenStreetMap, from your old data models, and we have all the semantics like buildings, roads, or kind of facades or bridges, and then user will try to put on logic on top of this application for the all purpose. And for this one, this is our first test. So we try to do solar envelope computations. So we take that plugin, we build a simple application. That's where we want to compute how much shadows on top of each roof of each building. That is solar envelope, because sometimes a building can block other building roofs. So we can put solar panels on top of that. So this is one way to study. For this one, I apologize that I don't have the demo here, but it's actually run very sweet and nice, but I don't have the data with me today. Next time I will bring. So when we're sliding the slider bar on top, those will change the shadows, the sun positions, they will have the shadows cast instantly on these type of buildings. So instead of doing offline computation, we can do it online really quickly with this type of tools as well. So these are the type of things that we would like to follow next. Of course, there are challenges in using game engines because they're not designed for data-driven task. So most assets are backed statically. So which means like if you have data that change for impact analysis, you would have to change to the pipeline of Unity or the game engines. So we actually make that change in our plugin. And also to integrate components from different data sources, from NYC Open Data, or from OpenStreetMap, or from other geometry. We need a way to actually for them to talk. When I get a building, I need to know, is it actually a building or it's just like a shape of a block? So we need to determine those. And then of course there are also like two type of game engine, Unity and Unreal engines. So we pick Unity 3D because those are the most popular one for indie game developers, like independent game developers. Because our target again is those that actually being taught a lot in the media program, so that they can go out and help the experts. That's why we pick Unity over Unreal. But it should work for both in principles. And this is some discussion that we have on the data type, but I might have out of time. So I'm just saying that, so when we add data capability into the game engines, we have different type of data in urban. We have like CSV, GTFS, JSON, all type crazy data format, data exchange. How we make sure that whatever we build, user include into the game engines can actually be integrated correctly, appropriately. So we need a common data standard for data exchange. We need semantic data. For that, we look into CityGML, which is a standard to describe cities. They can describe buildings, they can describe infrastructure, and they are also like other movement to actually add like sensor data or other type of data into this CityGML. And they backed by a consortium, which means they have standard. They keep it going out. We have followed some standard. So this is our final solution at the moment. So it's still an ongoing project, so we hope to have results very soon in next year. Hopefully the plugin itself to be released as open source. But we're going to combine CityGML, Unity 3D, and we're adding computing power on top of Unity 3D. That's a different product I haven't talked about at all in this talk, but that's also different efforts. So we're going to evaluate our plugin in a classroom environment. So I'm going to teach an urban visualization class. So in that class, I will, instead of using D3 or the typical web design for visualization, I'm going to use Unity 3D. And at the end of the class, the student will try to rebuild urban again using our plugin. Our goal is that each student should be able to build an application like that in just one semester time frame. And that is our vision. So hopefully we have results to report soon. So the fun part is that when you go on with game engines, you can actually go with reality, like this HoloLens, for example. So we also get our model onto this HoloLens. I can just mapping things around. So it's just cool and fun to watch. He will say something. But maybe not.
Rotate model.
He does. Yeah. Because the HoloLens only take a voice command. You cannot control much with rotation. You have to say rotate models to rotate the model itself. So this is our framework on the HoloLens.
Change light.
Oh, okay. He said again, so never mind. So it's just something fun to look around. And also we try to deploy this framework on this text TVs on our scalable display. We have 60 monitors 4K for 400 megapixels. It's really large screen. So we would like to add this type of thing to Unity 3D as well, but that's different type of work, as I mentioned. Okay, so I'm almost there. So in conclusions, so I want to say that our goal is to make big data analytics to reach to a large audience, non-CS or non-expert audience in both usabilities and development. So they should be used by non-expert users, and if an experts group want to build an application, they shouldn't need to go through the hassle of hiring very expert in developing graphics engine. They should go straight to someone that can build an application, visual applications. That's our target. And while we're developing these applications, we say that we think the boundary between different disciplines in the area like information system, database, or visualization almost like blurred, because we need all of that in a visual analytic applications. And for that, when human in the loop, we also need interactivity. And for us, all our projects, we always have a partner, a collaborator, so we really value our collaborators. It's almost critical, because without them, all our work cannot be done. Because I remember that the first time I built the mapping engines for our tools, it looks really ugly. It looks like just like a gig, just all the features put in there, but it's actually no use. After go through a lot of process with the clients or with our domain expert, they improve a lot. It looks much nicer. So they actually help us a lot in the way we build applications. And before I conclude the talk, I just wanted to acknowledge that many of this work, we have a lot of collaborators, and John worked with many colleagues at NYU, CUNY, also at NYU CUSP. You would notice that there's a lot of Brazilian on the list, because my advisor is Brazilian, so I work with the groups. During my PhD, I know a lot of friends in Brazil, but I don't speak Portuguese. That's so sad. But anyway, so I would like to thank you for listening to my talk, and it's really a true pleasure to show the work. Of course, I'll be happy to answer any questions. Yeah.
So thank you, Rui, for your great presentation. So now we have time for questions.
Hello. So I was really curious about when you first showed XIV, you said you have public data of the rights, it's available. Are there some sorts of concerns with the privacy in the sense that now where you can analyze, for instance, in your system, patterns in where people pick up and left off? Does this raise some concern for some people? Because now you can actually, for instance, find a pattern of, like you showed in West Village, right? So could I, for instance, analyze a specific building in West Village? Is this something that can become a concern when you have like large visualization tools for urban data?
Yes, that is a really big concern. The thing is that this project started in 2008, so by then, at that time, there was not much concern. So the data published at that time was public, and including the data on the actual medallion of the drivers, so there's no masking out, so you can actually track each driver at that time. But then in 2013, they started looking into that. They tried to do the masking of the medallion, so we cannot track the drivers anymore. But they did make a very huge mistake in the masking, because they used the default sort when they do the hash. So actually, you can look through the available medallions, do the hash, and revert it back. You actually can track the drivers. So there was an article saying that there was a flaw in the way they hashed the taxi medallion. And then in 2014, they fixed that. But still, if you really want to track a taxi, you can go into a taxi, put in a very, very unique tip. Let's say, I want to tip $1.01. And then next year, you look at the data available online, you will see that that's the trip you took, because it has a very unique tip amount. So because of that issues, they now do aggregated data. So the data we have here is actually the one we have connection with them, so we have proprietary data with them. The public stream is now very, they're really concerned about privacy, so they actually aggregated the data now. Yeah.
Pessoal, quem quiser fazer pergunta em português, a gente traduz. Alguma curiosidade?
I have to apologize, I speak really fast. Even though Shayla already remind me of that, but I somehow, in the middle of the talk, I start speed up. And I didn't, it runs in the family, sorry.
Rui, I would like to ask something about you showed to us how it's difficult to analyze one kind of data, okay? Just for instance, cab data. So the challenge is to integrate and analyze two or more kind of data, and how they can contribute for the governmental authorities, or how make our society be less excluded, for instance. How do you think that the contribution of urban big data can be improve our society?
Maybe that's a long question. So you're saying that, so now if we do like multiple data sets, how does it help?
Yes, yes.
So actually the value of data is never coming from one data set. It's really almost invaluable, like not really valuable. So it always comes with combined multiple data sets together. So that's our strategy. So if you look at that, except for the taxi CVs, which is used for exploring the taxi, a single data set, the rest we have multiple data sets together. So because we believe that the values really only comes when you combine multiple data sources. Is that, I think I missed your question, sorry.
Yes, yes. No, this one is more out of a reflection about how urban big data can be our society less excluded, because we are an excluded society, in an economical way, in a social way. So how can this kind of research can improve us as a less excluded society?
As less?
Excluded. Because we have rich people, we have poor people, we have people who has access to technology, we have people that haven't this access, so this kind of thing.
So actually, at CUSP, we started out as a, so the data facility at CUSP, at first started as physical facility, so we need people come to the data facility to do analysis, but now we actually moved that to the cloud. So things now instead of actually, so you can think that as a way to go from HPC to big data, instead of bring compute to data, now we bring compute to the users. So now if we have a user with interest, we can actually allocate some resource for them on the cloud, so they don't even need their own machine to do analysis now. So now we call something called ADRF, Advanced Research Center, so which means you have a number of people and you select the data source, you specify the resource, you can allocate just like Amazon Cloud Service. You have your own silo to do data analysis. We think that way we don't really rely so much on the users have the physical capabilities, but now it's falling on the data facilities. I hope that answers your question.
Yes, yes, thank you very much. Pessoal, mais alguém com alguma pergunta, alguma curiosidade?
Thank you. Thank you again. Thanks.
Bom, pessoal, agradecemos então a presença de todos. Aguardamos vocês amanhã. Lembrando que à noite nós temos o jantar de confraternização na Galeteria do Lago. Quem ainda quiser participar pode conversar conosco amanhã pela manhã, no máximo. E voltamos daí quinta com a palestra, o Keynote Nacional, falando sobre ética e sustentabilidade em sistemas de informação. Obrigada e boa noite a todos.